Hello, everybody. So today I'm going to be talking about how we built a message queue system on top of HBase to power Box's public events API. So before I get started, a bit about Box, who we are, what we do. So we're an enterprise cloud content management company. And so our goal is to provide our customers with a platform that allows them to share, manage, and access their content anywhere from any device. So what is our public events API? So basically, it's a real-time stream showing all of the activity that's happening inside a user's account. So whenever there are any uploads, downloads, moves, renames, deletes, et cetera, that happen on content that a user has access to, we'll log a event to that user stream telling what action happened and who performed it. So here's an example events API request. And the important parameter here is the stream position. Because the model that the events API exposes is basically of an ordered stream of events. And so the way clients interact with it is they keep track of where they are in their stream, and they issue fetch requests for basically all the events in the stream after their current position. The system then guarantees that any future events will get logged to higher positions, so that clients can basically then when they come in with their next stream position, they can get the new events. So two important properties about this system are that it's persistent and replayable. And so what I mean by that is that we keep events in a user stream for up to a month. And at any point during that month, a client can basically go back to previous stream positions that it had already consumed and basically re-consume the messages in the stream. So why did we build it? So basically, we thought this would be generally useful for our third-party developers. But internally, our main driving use case was to power our desktop sync client. So at the time, our desktop sync client had been operating in a bit of a batch mode, where in order to figure out what had changed on Box and to then pull those changes locally, it had to get a full snapshot of your tree on Box, pull that locally, and then do a diff against what it had on the local file system. And so this wasn't particularly scalable, either on the server side or on the client side, especially when you consider that some of our customers wanted to be able to sync file system trees that had upwards of hundreds of thousands of files and folders in them. So we wanted to switch to a mode where basically the sync client got a notification saying, for example, that a file had been uploaded in a specific folder, and it could just go ahead and directly download that file. So a couple of interesting requirements arose from the sync use case. First, we really need to have guaranteed delivery, because if our sync client basically doesn't get a notification, if there's no way for it to know about that a change happened on Box, there's no way for it to apply that change locally, and your sync client's broken. Local will be out of sync with Box. It's not uncommon for clients to be offline for days or even weeks at a time. A employee goes on vacation, leaves his work laptop at home powered off. And when you combine these two, we felt we really need to have a system that had a strong persistence layer, because if you need guaranteed delivery, but you can't rely on your clients being online to receive and act messages, you need to really be able to persist those messages until the client comes back online. Also, you can run a sync client across multiple different devices, and they all need to consume the same stream of events from the user, which is where we really need to have this replayability. Because just because the system has handed out an event to one sync client on one user's machine doesn't mean it doesn't have to hand that event again to another sync client on another machine. So how do we implement? So the basic architecture is we start with our MySQL DB tier, where we actually have a table in every MySQL database where we log messages transactionally with the actual modifications associated with that event. And the reason we do this is because we really want to have the guarantee that we both never have a actual change made without logging an event, and we also don't ever want to log any phantom events that where the data modification actually eventually got rolled back. Because both of those, if you don't send the event to the sync client or send an event that doesn't correspond with an actual state change, you'll drive your local sync client kind of out of sync. And currently, we're doing about 1,500 events per second at peak across our MySQL DB tier. We then basically have a process that's responsible for connecting to all of our MySQL databases, reading these tables, reading events out of these tables, and dispatching them to a pool of machines who do the calculation to figure out, based on this event, who should be able to see this event, who should we send it to. Once it gets results back from those machines, it actually writes the event to each of the user's queues, which we store in HBase. Then when clients want to come in, which we're doing about 25,000 events per second at this level after you do the fan out. And then when clients want to come in and do reads and issue requests against the events API, basically we then go and find that user's queue in HBase and do the read there. So how do we actually store these message queues in HBase? So a quick overview of kind of the HBase data model. Basically, data is organized into rows, each of which has a unique row key. These rows are then organized into tables, which are lexicographically ordered by their row key. And then the table basically gets split into regions based off its row key space, and those get distributed across the HBase cluster to allow you to scale. So if you got an HBase key space for a specific table, and then your actual node serving HBase at the bottom, the HBase key space gets divided up into various regions, and those get assigned to your various region servers. So to store queues inside this data model, we basically assign a section of the HBase key space to each user. Then within that key space, we make sure that messages get stored as rows inside that section of the key space, with older messages being lexicographically earlier in the key space than newer messages. At that point, we can take advantage of HBase's scan API to take a position, map it directly to a specific row key in a user's queue, and then retrieve all of the events up to the end of the user's key space that are in HBase for that user. So the specific row key structure we use is, so we start with a fixed pseudorandom prefix for each user. It's just the first 2 bytes of the user ID of the SHA-1. And we do this to make sure that all of our user queues can kind of be evenly distributed across the HBase key space. Because if they're evenly distributed across the HBase key space, they'll be evenly distributed across the various regions, which means they'll get evenly distributed across the various region servers actually serving our traffic. We then have a user ID, which is what actually demarcates this section of the key space as belonging to this user. And then we have a position which provides that ordering so that older events will be earlier in the key space and later events will be later. And for this, we actually use a millisecond timestamp that we allocate right before writing an event to HBase. So there are a couple of pros and cons to using timestamp as our queue position. The biggest pro is it's really simple web method of giving us roughly monotonically increasing positions, and doesn't require any coordination to happen between our various write requests. On the downside, it's actually not enough to guarantee that we have append-only semantics if we allow parallel writes to a queue. And we need to have append-only semantics to actually guarantee delivery. And so here's how this can actually happen. If you have 2 writes coming in parallel, one to position 1 and the other to position 2, the write to position 2 can actually complete first. If you then have a client come in and do a read, he'll see event 2, but he's not going to see event 1 because it hasn't actually been written to HBase yet. At that point, the write to position 1 may eventually succeed, but the client will have already advanced his stream position, so he's never going to actually pick up that event. So how do we solve this problem? So the basic problem we need to solve is we need to make sure that clients never advance their writes, advance their stream positions past writes that might eventually succeed. But we do need to allow them to advance their stream position eventually, although theoretically every client could just always come in and start reads from 0, and they would actually pick up every event. That's obviously not going to scale as you have more and more events in your stream. So how do we know when it's safe to advance the position? The solution we came up with is to do time bounding of our writes and then backscanning of our reads. So what we mean by time bounding of our writes is that from the moment where you allocate a position, a timestamp for a specific row, to the moment that write completes at the HBase level, that needs to happen within a fixed amount of time in order for the write to be considered successful. And so if it's not successful, just like any other failure, we don't guarantee delivery. So if a client wants that message delivered, he'll have to retry at a higher stream position, just like he would for any other failure. On the read side, we then basically limit how close to the end of the queue a client can actually advance their stream position. Where the end of the queue is current time, we actually won't let them advance their position greater than current time minus this backscan interval. And by making that backscan interval greater than or equal to the write time bound, we assure basically that any position the client is advancing past is, if there are any pending writes to that position, we know that they are already greater than their write time bound, which means even if they eventually succeed at the HBase level, at the client level, they'll be treated as failed. And so it's safe to move past them. So this does provide guaranteed delivery, but it does come at a bit of a cost of a substantial number of duplicate events, because as you're backscanning, you are rescanning a section of the HBase key space potentially multiple times, and you're going to resend to the client any events that happen to be in that section of the key space. Cool. And here's a diagram basically showing how this works. Let's say you've got a write to position 3 that's already happened. You've got 2 writes that are in flight to positions 1 and 2, but they're still within their time bound. A client comes in and does his read. He'll pick up the event at position 3. He's not going to be able to advance his position, though, because positions 1 and 2 are still inside their time bound. Suppose then the write to position 2 completes within its time bound. The write to position 1 actually doesn't. A client will come in and do its read. It'll pick up position 2 and 3, and this time it will actually advance its position, since position 1 is no longer within its time bound. At some point, the write to position 1 might complete successfully. At the HBase level, at the client level, though, we'll treat it as a failure, and we will write it again to a higher position. At that point, when the client comes in and does read, he'll actually be able to pick up this event. So far, I've talked about how we implement these queues in a single HBase cluster. Obviously, we need to be able to replicate these queues to other HBase clusters in other data centers, so that if we ever have to take a cluster or data center offline, either for maintenance or in the event of a disaster, we can still remain available. So we have a basic master-slave architecture where we have 1 cluster per data center. The master cluster handles all reads and writes, and basically all our slave clusters are just passive replicas that are waiting to be promoted. And so when we do a promotion, we transparently fail all of our clients over to the new master cluster. And what I mean by that is we take the clients who are issuing fetch requests with their particular stream positions against one master cluster. We'll start issuing those fetch requests from the same stream positions against the new master cluster. So unfortunately, native HBase replication isn't actually enough for us. We can't use it directly because it doesn't have the right consistency guarantees that we need. Specifically, if you allow clients to fail over to a lagging cluster, they might potentially miss events. For example, suppose we have a master cluster on the left and then a slave cluster on the right, and we have a bit of replication lag, so the event at position 2 hasn't yet replicated. If we do a failover at this point, we can have we now open up a new cluster to both writes and reads. At this point, when the client comes in and does his read, he's not going to get the event written to position 2 because it hasn't yet been replicated. At that point, he may have actually advanced his stream position past position 2, and so when HBase eventually does catch up and replicates that event to position 2, it'll now be behind the client's read frontier, and he'll never get that message. So what we need is a replication system that's aware of these master-slave failovers. And specifically, we need one that when you do a master-slave failover, you stop exactly replicating your messages, and you start appending them to the current ends of the queues. So again, suppose we have a master cluster on the left and a slave cluster on the right, and we have replication flowing between them. When we do a failover, we have the same scenario before. We have a new write come in, and we have a client do a read. But this time, because we're replicating into a newly mastered cluster, we write it to the end of the queue. So when the client comes back and does a read, it actually picks up that message. So the first method that we basically did to implement this replication was we piggybacked on top of MySQL replication. So as we had that architecture diagram before, we've got our MySQL DB tier, which is already replicated across all of our data centers. We then duplicate basically our event processing pipeline in the master data center and the slave data center. In the master data center, you're responsible for reading the events out of the database and then allocating a position. And then once you've actually successfully processed the event, you write whatever position you allocated back to the MySQL DB. On the slave side, you're now looking for events that have had positions allocated by them in the master cluster, and then you're rewriting those events using that master position. When you do a master-slave switch, before the slave data center basically starts operating in master mode, it clears out any non-replicated events and resets them so that it will then allocate new positions for them. So what are the problems with this approach? So one substantial one is we only have basically one column in the data base per event where we can write a position, which means we can only allocate one position for an entire event. And this is regardless of how many users we have to send it to. Which is problematic because some events actually need to go to upwards of 100,000 users. We have larger customers who want to have folders that basically the entire company has access to. So the entire company would get notifications about what's happening in that folder. And then because we have this model where we have to enforce strict time bounds around all of our writes, we can't possibly do an arbitrary large number of writes to an arbitrary number of user queues within a fixed time bound. So we tried to basically work around this by adding a secondary MySQL table where we could actually, after we calculated the fan out, we could basically chunk up all the users we had to send the event to, create separate rows for them, and actually allocate a position for fixed size of events of about 1,000 at a time. Which worked. It allows us to scale up to higher to fan outs for these user queues, but on the flip side is it really adds a lot of extra write load on top of our MySQL cluster. The other big problem is that the replication is pretty much implemented entirely at the client level, which means you can't really open up any other clients have write access to your queues, because at that point they'd have to duplicate all of your replication logic. So what we'd really like to move to is an architecture that looks a little bit more like this, where we have an actual service fronting our HBase cluster that implements a queue API, basically append and fetch, which is what then all of our dispatchers writing to the queue and our clients reading from the queues interact with, so they now don't have to know anything about how the queues are actually stored in HBase. And then we want to have this queuing service basically be responsible for shipping all of the replication, basically all of the events written to the queue and all of their positions over to its slave cluster. So basically, implementing the fetch and append API is fairly straightforward. It's just copying code that we already had in our clients, moving it into a service. So we need to figure out how we're going to be able to do this replication API. And so one possibility is, can we actually leverage HBase replication? And we know HBase replication on its own won't have the right consistency guarantees, but can we use it at least as a stream for shipping all of the changes from one cluster to the other? And so in fact, we think we can. So HBase replication employs a master push model, where basically the master cluster has a configured set of slave servers, and it pushes all of the changes that are written to its write-ahead log to each of those slave servers. So if we can get this queue service to actually be able to talk the native HBase replication API, we can actually configure it to be and acting as a slave HBase cluster, at which point our master HBase cluster will send it all of its write-ahead log changes. Which then gives us the opportunity to basically hook into the HBase replication stream and enforce the master-slave behavior we need, where if you're replicating to a master cluster, we append at the end of the queues. If you're replicating to a slave cluster, we actually replicate the message at its original position. So right now, this is actually what we're currently working on, trying to port over from our original architecture onto this architecture. So once we finish that, what would be next for the system? And so one significant problem is that we still have this fire hose of kind of all the user activity that's stored inside these MySQL tables, where it's not very easy to access and work with, but it's really useful data. And so the problem is it's really expensive to add new subscribers onto these MySQL queues, primarily because for every subscriber you need to add on, you need to add a new column so you can track their processing status. You're adding extra write load onto your MySQL DB, again, to track their processing status. And you also open up this pretty bad failure mode, where if a client goes offline, you're put in a position, because you can't actually remove any rows from this table until they're processed by all clients. If you have a client offline, you either have to sacrifice your delivery guarantees to that client, or you're going to start churning through a lot of your storage on your main MySQL DB tier, which obviously, if you let that go on long enough and the client never comes back online, you're eventually going to run out of storage on your box, and then you're going to escalate to the database being down, which would be very bad. The other problem is it's sort of expensive to add new events to the stream, because each event has to be a write, again, to your MySQL DB tier, which is particularly problematic when you have these if you have non-DB transactional events, like downloads or logins, that would normally be read-only, because now you're turning them actually into a DB write operation. And so what we'd like to do is we'd like to actually keep MySQL so that we could actually have it be the initial record for any of these transactional events, so that we can continue to have that good, strong guarantee that for transactional events, they'll never be logged unless their actual associated modifications were applied. But we want to have a separate system that we can use basically to actually expose this Firehose stream to all the clients, where it'll be really easy to add new clients onto the system, and also basically a client going down wouldn't cause any impact to the other systems, and it will also be the place for the initial record for any non-DB transactional events. So one possibility is, could we actually do what we did for our user streams and actually build a queue on top of HBase, powering this Firehose stream? The big problem here is it's got a much higher throughput than our existing user queues. And because basically the way we've laid out our queues in HBase, all the writes to a queue are going to go to a very small section of the HBase key space. They're all pretty much going to line up on one single region server, which means it's easy to basically, for a very busy queue, to have too much write traffic going to that region server and knock it over. So at minimum, we probably have to, if we want to do this, we would have to support partitioning topics. So we could basically take the queue, spread it up to different sections of the HBase key space, so we can actually distribute them across various region servers in our cluster. Conceptually, it's pretty simple. We just need to incorporate a partition ID into our row key. It looks probably something like this. We have a pseudorandom prefix. Now we have a topic ID, a partition ID, and a position. And we just need to make sure that the pseudorandom prefix is unique per topic ID, partition ID pair. If you keep it just unique to the topic ID pair, you're still going to put all of your partitions right next to each other in the key space. The other kind of more substantial problem is that if for the higher throughput queues, we might actually have to get away from using timestamps as our queue position, which would be a pretty substantial change to how we've been doing queues in HBase so far. And the reason is our backscan algorithm, the number of duplicate events that it generates kind of scales proportionally to the throughput of the queue. Suppose you have 1,500 events per second, and you're using a 5-second backscan, which is about what we're using right now. That's going to be 7,500 duplicate events every time a client does a full set of fetches across all your partitions, which is a pretty large number of duplicate events for a client to have to deal with. So if we want to continue to use timestamps, we're really going to have to be able to shrink our time bounding and backscanning intervals down quite substantially, which we may be able to do because one of the reasons why we had such high backscan intervals in the past is because we had to deal with one position for a whole chunk of writes. Now, once we have replication inside the queue service itself, we can actually have one position per each write, which should be able to move those numbers down quite a bit. But we'll still have this problem where if we try and go down to like millisecond backscan intervals and such, we're getting to the point where we have to consider more seriously about clock skew between various machines. And it's not clear yet if our timing infrastructure that we have in our data centers is robust enough to handle that level of clock skew. So are there any open source alternatives we could use instead? And so there is one obvious one, which is Kafka. It's got a very so it's the closest off-the-rack queuing system to what we've built. Developed at LinkedIn, open source in 2011. Really built to power LinkedIn's analytic pipeline. It's a very similar model built around what they call ordered commit logs, and they did it for very similar reasons, which is basically to make it really easy to have add new subscribers on the stream and to be able to support subscribers that consume from the stream at very different rates. Some consume in real time, some consume once an hour, some consume once a day. And so the slow subscribers don't cause any pain to the other subscribers in the system. So using Kafka would make a lot of sense because it's a dedicated queuing system. It's a lot more fully featured than what we've built so far, and it's tuned for much higher throughput. So why wouldn't we use it? So the first problem is to be a second system we'd have to maintain because it couldn't actually replace our initial HBase use case. And there's a reason why is it can't scale to millions of topics. So for our user queues, we've got 3 different queues for every user, which each has a different filtering of the events that they have access to. And we've got 30 plus million users currently. So we're looking at 90 plus million queues that we have to store. Currently, Kafka tops out in the range of tens of thousands of topics or partitions per cluster. And in general, its design requires very granular topic tracking, which is always going to be a barrier to scaling up to more topics versus what we have in HBase. HBase cluster doesn't know at all about the topics. We're just basically sectioning off the key space at the application level. And so this would be OK, basically, we basically got to have 2 use cases. One, low throughput but very high topics. The other is low topics but very high throughput. It would sort of make sense to have 2 different systems to support those 2 use cases. But we do think we eventually want to support basically a medium topic to medium throughput case, which we'd have to build in a lot of the same support we would for the low topic, high throughput. And that would be if we want to do basically a stream of events per enterprise, which would be pretty useful for our customers. And there basically we have, right now we have over 50,000 enterprises who use us. So we'd have to have over 50,000 topics. And the throughput wouldn't necessarily be large enough to knock over an HBase cluster. It would still be much larger than what we have currently, and we probably wouldn't be very comfortable running all that throughput against a single region server, especially because it would be danger of having a few busy topics for our larger enterprises land on one region server and then knock it over. There's also one slightly more difficult problem to overcome if we wanted to port over Kafka, and that's its intercluster replication support. And the problem here is you don't have enough control over the positions Kafka uses internally to actually guarantee that if you were replicating events from one cluster to the other, that you could actually take a client who is reading against one cluster, swing it over to the other, use the same stream position it had originally, and have it not miss any events. And this is especially true if you have any sort of lag coming in between your 2 clusters. So as you see here, if we had a master Kafka cluster on the left and a slave one on the right, we're doing some external replication to actually ship the events between the 2 clusters. We have a client come in and do a read against this cluster over here. He's going to basically advance the stream position to after event 3. If you do a failover, when you do a write against the Kafka cluster, it's going to just allocate a position for that new event relative to whatever the current end of its log is. So if this cluster is lagging, it's going to do that new write to position 2. And when replication catches up, it would write those new events to positions 3 and 4. So if you then had a client come in with that same position it had against the original cluster, do a read against here, he's going to re-pick up against that event 4 that he already picked up at the original cluster, but he's never going to see that event that was written back to position 2. So wrapping up, what we've been able to do is we've been able to leverage HBase to store millions of guaranteed delivery message queues, each of which was replicated between data centers and independently consumable by an arbitrary number of clients. We're currently working on trying to build a cleaner abstraction around these user queues and actually be able to support native replication without having that be implemented at the client level. And then we still need to decide. So for this Kafka use case, we have some ideas about how you might be able to change Kafka to support this intercluster replication. We haven't really done a deep dive into it to see if it'd definitely require changing some of the guts of Kafka. We haven't really seen if that would be changes that would be something that would make sense for kind of the direction of the project. Or if we took that route, we'd have to basically maintain a fork forever. And then whether or not that, or if we're continuing to build on top of HBase, is really the right strategy for supporting these higher throughput queues. So that's all I've got. I think we have a little bit of time for questions.
Yeah. We'll take a couple of questions now. So, any questions? Yeah.
When you're replicating from a fallback, you fall into a new master server,
yep.
and the events from the old queue are being written to the new queue as new writes are coming in.
Yep.
You have a reordering issue potentially.
Yes.
Is that an issue for clients, or do you reorder within the look-back period before sending it to the client, or how does that work?
So basically, yeah. So the guarantees of the stream is that the stream is ordered so that you can have guaranteed delivery, but there's no kind of semantic meaning to the order of the stream. So basically, events can come out of order logically to clients from how they occurred on Box, and it's up to the client to basically do any reordering that's necessary for their particular use case.
So does it create and delete? Put them out of order, it matters.
Yes, so we actually have the information encoding in the event. So for every object in our database has what we call a sequence ID, which is basically a version of the state of the object. So inside each event, we actually have the full state of the object that as the object was after we applied that change. So basically, if you have a create and delete, you'll have a create with a sequence ID of 0, then a delete with sequence ID 1. So if a client basically gets those two events, it can say, OK, this one happened first, this one happened second.
Next question. OK, then we'll have the office hours also outside.
Yep.
And now we'll move on to the next one.
Cool.
Is Varun around?